You are looking at pypy.org. Here you can find thousands of Python packages. I have just made my first package and I want to show you how I did it. The package allows me to show directory trees from the terminal. I know there already are such packages, but I needed something special. I want the tree to be sorted alphabetically, but first by directories and then by files. And I want to be able to exclude items from the output. Let me show you what it does. I pip install tree from pypy. Yep, that's 3 E's. Now this package can be used from Python code, but also from the command line with this command. Just like that. In this tutorial you will learn how to create this Python package. You learn how it is structured and how to test locally. Then how to build it and upload to pypy. Then how to install it, run from existing code, and finally directly from the command line. Let's go! So I started with my first package, and my, what an adventure! In fact, there is so much to tell that I split it up in 3 parts. Local packages and the import system, developing and building distributable packages, and published packages on pypy. This is part 1. In this part you and I will do some detective work. You see, Python packages might not exactly be what you think they are, and in order for you to learn how to create distributable packages, you first need to understand modules, packages, and namespaces in Python. Let's start with modules. Look at this project. It has empty file module1.py, and it has main.py with this code. I execute main, and this is the result. This is the first import variant where I import a module from the same folder as main. You have probably done something like this many times. So what happened? The import system was instructed to import module 1. It found module1.py and created a module object from it. But in fact, the process was a little bit more complicated. What happens when module 1 is not a Python file, but a folder? I delete module 1 and create folder module 1. I execute again. So this time, module 1 is a folder and the output is a namespace module. You can see that between the round brackets in the output. So what happened this time? Python's import system will check if the target is a file or folder. And in case of a folder, a namespace module is made. Unfortunately, both the names module and namespace are very ambiguous. Let me start with the word module. The word module is used for any unit of code, for example, a function or a class. But this is not the type of modules we will talk about here. The second thing that is described with the name module is a module file. These are Python files meant to be imported. From the Python file, a module object is created. So what is important when dealing with the import system is that module objects are created from module files. But this picture is not complete yet. You already saw that the first module object was created from a module file. And the second module object was created from a folder. When the module object was created from a folder, it is known as a package. So when the origin of a module object is a module file, I will call the module object a module. When the module object is created from a folder, I will call it package. But it gets more confusing. Let's do another experiment. I add module1.py again. Now there is a name conflict. What will be imported? Apparently the file took precedence over the folder. In fact, this behavior is described in PEP 420. The import system searched for folder module 1. There is a folder module 1, but it does not contain dunder-init.py. It continues to search for module1.py, which is present. A module object is created from it and returned. We'll look at the rest of the process later. First, I am curious about the influence of dunderinit.py. As you may know, before Python 3.3, dunderinit.py was required in order to make a folder into a package. Although this is not needed anymore, dunderinit.py still plays a role in the import system. Let me show you. Look at the output. The module object was created from module.py. I add dunderinit.py and execute the code again. This time a package was created. Again, technically it is a module object, but since it is created from a folder containing dunderinit.py, it is regarded as a package. So indeed, by putting dunderinit.py in folder module1, it got the highest priority and a package was created from it. Module1.py, which has second place in this order, is ignored. So now you already saw three kinds of module objects. There are the ones created from Python files, from folders without dunderinit.py, and from folders with dunderinit.py. From now I will call them module, namespace package and regular package. So, what are their purposes? A module contains code like functions and classes. A namespace package contains modules, and so do regular packages. And that leaves the question, what is the difference between a namespace package and a regular package? Well, I'll come back to that soon. First, I must explain namespaces. By the way, I put everything you see here in an ebook and a link to it is in the description. The ebook contains a step-by-step description how to make packages, test them locally and publish them on PyPy. And since the terminology of Python packages can be ambiguous at times, I made sure every topic is explained with clear definitions, including namespaces. Look at this project. There is a folder called package1. In it, there is empty file module1.py. Here is main. Notice I import package1.module1. When I execute the code, this is the output. You have already seen this. Package1 becomes a module object. This is the first module object that has been created from the import statement. Let me show you what is in it. You are looking at a namespace. A namespace is a dictionary with all the variables in the current scope. And the scope that I pass to the built-in vars function is package1, and these are its variables. Notice module1 here. That is the second created module object. By importing package1.module1, two module objects were created. First, there is package1. Package1 has a namespace, which contains a key referencing module1. So, the module objects have a parent-child relationship. Module1 also has a namespace. Let me show you what is in there. I print the namespace of package1.module1. Module namespaces are very verbose. All that is interesting at this point is that you are looking at a dictionary with all the variables of module 1. Now I add a function to the module. I execute the code again. Look at the output. Key f1 with value function object has been added to the namespace. Module objects allow us to access namespace variables with the dot syntax. That is why I can do this now. Now, by the way, I had a question at this point. Notice that f1 becomes available without explicitly importing it. Does that mean that module 1 will also be automatically available when I just import package1? Nope, that does not work. Apparently, the functions and classes in a module are stored in the module's namespace automatically. But modules do not become a part of the packages namespace automatically. I can show this again with the vars function. There is no module 1 here. And when I add module 1 to the import statement, it will be added to package 1's namespace again. And if you think about this, it makes sense. Why would importing the root name implicitly load all the modules in it? That could blow up things fast. Until now, packages were created and found in our local project folder. But actually, multiple locations will be searched when importing in Python. And this is closely related to the difference between regular packages and namespace packages. The first thing you need to know is that their names are extremely badly chosen because they do not express what they are about. Namespace packages are composed of one or more source locations, and regular packages come from a single source location. This led to two other questions I had. First of all, why spread a package over multiple locations? Well, I just worked for a big company that uses notebooks for their data science projects. The employees often import public packages from PyPy, but also private packages from an internal network share. But instead of copying the packages manually to their local project folders, the path to the packages are injected into the Python module search path. Now, the module search path is initialized when Python starts. Here is how you can check its entries. The first entry is the path to my local project. By the way, that is the source of many Python beginner programmers' frustration. If a beginner wants to experiment with the datetime module, but accidentally names the test script datetime.py, it will overrule the standard library datetime module. When the local datetime script now imports datetime, a circular import error is raised, leaving the developer with many question marks. But back to sys.path. The next three entries are variations of the standard library files. Their differences are not important for this tutorial, since it is highly unlikely that you're going to change the contents of these paths manually. Finally, there is the side packages folder. This is where packages are installed when pip installing without activating a virtual environment. By changing sys.path, it is possible to inject other paths in this list. One reason to do this is to search in private company network volumes. Let me show you. Package 1 is somewhere on the network and I want to import it. Let's see how this would work. Here is the project structure in the code editor. I create main.py. So how do I import module1.py? Well, in this test project I can do this. But this looks funny. First of all, this would be a very uncommon package name. And second, if this would really be a network drive, the import system has no way of finding it because the root package must be in one of the sys.path folders. So let me add it. Now I can omit the network location from the import statement. And that works. Let me show the path. And there it is. By inserting the location at index 0, it will be the first place where the import system will look for a package with name package1. Notice that the import statement now starts with package 1 instead of network location 1. Also notice the warning here. The type checker cannot resolve the import statement. This will only work at runtime. But don't worry, hacking paths into sys.path is bad practice anyway, and soon you will see a much better way to do this. But first I will show you what you can do with namespace packages. So, is package 1 a namespace package? Well, it should be. It is not a file and it does not contain dunderinit.py. Indeed, it is a namespace package. Namespace packages have a list of source locations. At this point, the list has a single location. Now, what if there are 3 network locations that all contribute to package 1? For example, 3 different developers maintain modules 1, 2, and 3. But they all need to be merged in package 1. No problem. I add the locations to the path in main. And import all their modules. And when I execute the code, the namespace package now has 3 source locations. Did you notice the order of the locations? Since I keep adding paths to the top of the list, the last inserted path will be the first one to be searched. At this point, there is a single package and its namespace contains 3 modules. As I said before, there is a scenario for this, and that is when the contribution for the package code needs to come from multiple locations. For example, when a company wants a single package from multiple sources where the root name is always the company name. In a closed ecosystem, this will work fine, but the system can also cause problems when the merge was not intended. For example, when 2 third-party developers both create a package called XLlib. What happens when you import core and worksheet? Yep, a single namespace package called XLlib is returned with modules core.py and worksheet.py. That is a Franken package. You probably want to avoid this. Now you can start by giving packages unique names. And you know that dunderinit.py can also play a role here. But here comes the sad news. None of the solutions is perfect. Let me explain why. Choosing a unique name might work in a controlled ecosystem like within a company. But when dealing with third-party packages, name conflicts are likely to happen. Even if PyPy requires unique pip install names, the package root name can still be anything. I will come back to this in the next part. First, it is time to add dunderinit.py to the system to show its influence. I'll use the previous example for this. Let's say that I decide that project 2 may never be part of a namespace package. Instead, it needs to be a regular package with a single source. So I add dunderinit.py. Now I ask you, what happens when I run the code? Look at the 3 import statements. Does it work? Do I get an error? And where? That is interesting. Dunderinit.py is in the second location, but when I execute the code, it is this statement that fails. What happened? Well, the import statement imports a package called package 1. It starts to search in location 3 because that will be the first one in the search path. Since package 1 in location 3 does not contain dunderinit.py, it will be marked as a candidate to contribute to a namespace package. Then the second location is scanned for package 1 and it is also found. But this one contained dunderinit.py, and the import system immediately returned a package containing only module 2.py. Then the import system tried to import the second part of the import statement, which is module 1. The returned package only contains module 2 and boom! Module not found error is raised. Now it really does not matter if you change the order of sys.path. Perhaps you can fix the current problem, but the system is unpredictable. In other words, you will only know that an import does what you expect if you test it or know exactly what search paths are defined and which packages it contains. So yes, dunderinit.py prevents packages from being merged with others, but A, it might cause other imports to fail, and B, since sys.path can be changed manually, it is very hard to predict what will fail exactly. And there are more things that can go wrong. For example, what if everyone decides that their package is the one and only package 1? The behavior of dunderinit.py is highly dependent on the order of paths in sys.path. The first one on the path wins. And since I'm inserting paths at index 0, I can even override Python built-in modules. So, dunderinit.py is a strange beast. Yes, it marks a package as being closed, but as you have seen, it does not always work. Or at least not always how you expect it to work. And soon I will show you a huge thinking error I made when I first created a package. But first let me come back to this overview again. You know that module objects can be namespace packages and regular packages. Namespace packages can merge package folders from different locations on the path. Regular packages have a single source location. Namespace packages cannot contain dunderinit.py. Regular packages must contain dunderinit.py. Namespace packages merge package modules from different locations in a single root namespace. Regular packages already have a single root namespace. Now at this point there is one thing really important to know. Everything you have seen until now falls under the category packages and works in local projects. It is independent of building, publishing and installing packages. For that we move to the second big topic of this tutorial, developing and building distributable packages. And to see how that works, click on this video. There you will see how to develop your package locally and build a distribution. You will also see what my biggest thinking error was when installing packages.